Okay guys, in this video we're going to be calculating the arc length on a given circle here that is intercepted by some central angle theta in the circle. And so what we're going to start by doing is just referring to our radian definition of an angle here. And so we say radian definition of angles. Recall that when we talk about radians, we define it using this format here. We say our central angle is equal in size to the arc length divided by the radius. And so one thing to keep in mind here is that this literally tells us that the angle is as big as however many times this radius length fits into the outside. So maybe one radius length, two radius lengths, 2 point something radius lengths here. But essentially that this arc length here could be determined if we knew already the angle in the middle here and the radius length, because we could solve for this arc length. And so to put this into context, we could say, well, to get arc length by itself, we would take both sides of this by r, multiply by r, and what we would get is this new equation that says r theta is equal to the arc length. Now, this is the same thing as our definition of angle measurement in radians, except for what we're doing is we're saying, I'd really care to find the arc length. So one thing I want to say about this formula, which is the formula for arc length, as long as the radius is r and theta is a non-negative radian measurement of a central angle of a circle, it says the length of the arc intercepted by the central angle is just s equals r theta. We want to memorize this formula here, but one thing I want to put into context is this. If we were to write out what this means, it means that the arc length is equal to the radius length, so the length of one radius, oh, I'm going to run out of room, you guys, times the number of radii that fit into the arc. Okay, so it's kind of like saying this. If, because I already know the angle, and the angle tells me how many times the radius does fit into the arc length, then if I were to say, let's take the length of just one radius here, which is this length here, and let's fit it into the outside this many times, well, then I could tell you the total length of that arc. And so using this definition, one thing to keep in mind, and this is pretty important for me, and maybe I'll type it because my handwriting is much better when I do type it, is that to find the arc length, you multiply the radius length by the angle expressed in radians. Okay, so I think the important thing here, for me at least, is that our angle has to be expressed in radians. Okay, and the reason behind that is just because if it's in radians, then that angle is telling you how many times this one radius length fits into that arc, and so we have to know how many times to multiply one radius length by, and so we got to have it in radians. So looking at this couple of examples that I have right here, let's go ahead and do that. The very first one just says a circle has a radius of 10 inches. It says, please and thank you, find the length of the arc. So find s that is intercepted by a central angle of 120 degrees. So I've already got my formula here. We say that the arc length is always just the radius length times however many times it fits around the outside. And I do have both the radius and the central angle here. And so if I were to like maybe conceptualize this here, we would say 120 degrees. Well, that's like 30 past a 90 there. I was trying to illustrate a 90. So we'd say, here's my central angle, 120 degrees. Theta equals 120 degrees. And we know that the radius length here is 10 inches. So basically what I'd like to do is go find s, of course, but if I knew this angle in radians, then it would tell me how many times 10 fits into this outside arc length. So the very first thing we need to do is this. Since we know the radius length is 10 inches and the angle is 120 degrees, we need to convert our 120 degrees here into radians. So remember that to convert to radians, we multiply by pi over 180 degrees. One of the first things that happens is our degrees cancel out here. And I recognize that 60 goes into both 120 and 80. So I'm going to go ahead and reduce these by factors of 60. 60 goes into 120 twice, and it goes into 180 thrice. So we get 2 times pi over 1 times 3. Our angle must be 2 pi thirds radians. And we don't have to write rad. We assume that it's in radians if there's no degrees there, but I'm going to write radians to indicate that that's what it is. So if I were to find the arc length now, the neat thing about it is this. We would say that the arc length is given as the radius, so 10 inches, times the angle in radians 2 pi thirds. Now 2 pi thirds doesn't look very fun. In terms of using it to find an arc length here, it's not very useful because, well, nobody talks in terms of multiples of pi. But what I do want to show you is this. If I were to take 2 times pi and divide that by 3, what this is telling me is that that radius length that you see here, 10, fits into this arc length about 2.09 times. And so it's got to be 2 times 10 at least, but we want to find an exact value here. So we'll start with our exact value. Start by putting our 10 over a 1, and we'll multiply straight across. We get 10 times 2 pi would be 20 pi, and on the bottom here, 1 times 3, and I'm just going to throw the word inches off on the side. So one thing that I want to make sure we write here is that this is the exact value of that arc length. Now, what we want to do is we want to get a decimal approximation. So that's what our calculator is here for. We'll go ahead and carry out this 20 times pi divided by 3 operation here. And what we get is about 20.94 inches. So I'm going to say that our arc length is approximately 20.94 inches, which makes reasonable sense given the fact that we knew that 10 inches here, this radius, according to the angle, fit into the arc length about 2.094 times. So 20.94 inches would be our arc length here. Now I want to try this again, and we'll take a look at checkpoint 8 here. It says a circle this time has a radius of 6 inches. So we say here's our central angle. Our radius is 6 inches. Okay. It says find the length of the arc intercepted by a central angle of 45 degrees. And remember to express arc length in terms of pi this time, and then round our answer to 2 decimal places like we did on the last one. So our 45-degree angle here, if I were to sketch this out, I know what 45 is about. It's about right there. Okay, so we say theta equals 45. So again, we could find S if we knew r times theta. Now we certainly know r is 6 inches, and we certainly know theta is 45 degrees. It's just that we want to convert 45 degrees into radians because that would tell us how many times 6 inches fits into this arc length around the outside. So again, we're going to convert this first into radians. Got to be in radians. Cancel out our degrees. I know that 45 goes into 45 once, and 45 goes into 184 times. So we get 1 over 1 times pi over 4. So a pi-4 radian measurement, of course, is 45 degrees here. Well, then our arc length would be this. We would say it's 6 inches, okay, our radius length, times the angle, pi-4, which in this case, if we were to multiply straight across, I am going to go ahead and cross-reduce here first. I know that 2 goes into both of these, goes into this 3 times and this twice. We would get 3 pi over 2, and we would want to just put our units off on the side. So this many inches. Now, again, if you're having a conversation with somebody, 3 pi halves inches isn't a really good number to throw about because nobody knows what that is. But if I were to actually convert this here and say, well, 3 times pi divided by 2, then I would get 4.71-ish, okay? So we say the arc length is about 4.71 inches, okay? There's our arc length. So arc length formula, it's just arc length is r times theta. You just need to remember, convert your degrees into radians if necessary, and then multiply the radius times the radian measurement of your angle, and you should have your arc length. Don't forget to label. Cheers.